So we want to be able to use calculus in order to locate and discover minima and maxima points of a given function. However, there's a few more terms that are in order before we proceed to our main results. And the first one is a very important concept called critical point. So a critical point of a function, so let's say x equals a. Let's say like this, a critical point of a function is a point on the domain such that either one, so basically we have two conditions that can qualify a point as a critical point. So such that either one, the derivative is undefined at that point, the derivative is undefined at the given point, or two, the derivative, of course, is defined and is equal to 0 at the point, at the given point. So, or when evaluated at the given point. So basically a critical point is a point on the domain of a function such that either the derivative is not defined, so in other words the derivative does not exist, or the derivative is equal to 0 at the given point. So there are basically three ways, because there's two ways for the derivative not to exist. So basically a critical point is either a point of discontinuity, in other words, there's some sort of hole or jump in the function, a point where the function, the graph of the function has a sharp corner, a point where the graph has a sharp corner, like that. So recall that this is one example of a discontinuous function, and that's another example. They're kind of squeezed together. So one that's just a function with a hole in the graph at that point. And then the other one, we actually have a jump. So it goes from one discontinuously to another output value. So recall that every differentiable function must be continuous. So if a function is not continuous, it cannot be differentiable. So whenever you have a hole in a function or a jump discontinuity in a function, the function fails to be differentiable. So saying the derivative is undefined, in other words, the function is not differentiable, that can happen either if the function is discontinuous at that point, or if there's a sharp corner or edge in the function's graph at that point, like there is in the graph of the absolute value of x at x is equal to 0. So recall the absolute value of x just looks like that. And then at the point x is equal to 0, we have the sharp corner. So that's an example where the function's continuous but not differentiable. So x equals 0 would be a critical point of the function absolute value of x. So those two cases, discontinuity or a sharp corner, describe the two main ways in which the derivative might not exist. And then, or the graph has a horizontal tangent line. So in other words, something like that. So at the bottom of this, you have this horizontal tangent line indicating that the derivative is equal to 0, because a 0 derivative means that the tangent line has 0 slope. So you can easily spot critical points just by looking at the graph. And of course, we can also figure them out analytically because they're all involve the derivative. So we compute the derivative, and either the derivative does not exist somewhere or the derivative is equal to 0. So by and large, the most predominant case that we see is the derivative is equal to 0. So typically we take the derivative and set it equal to 0. Of course, you always want to keep in the back of your mind the possibility that the derivative is undefined, and you want to spot those points too when you're looking for the critical points. So that's the definition of a critical point. So pretty simple. Now the next two are just types of points in general. So an interior point, or we can say x equals a is an interior point of a function if there's a neighborhood about x is equal to a. So if there is a neighborhood about x equals to a. And what does that mean? It just means an open interval containing a. So containing the point x is equal to a. So there's some open interval surrounding the point x is equal to a. So there's a neighborhood about x is equal to a that is entirely contained within the domain of the function f of the function. So the short way to write this is if there is an open interval u such that the point A is contained in the open interval u, and the open interval u is a subset of the domain of f. So dom f refers to the domain of f. So it's a set of all x values for which the function is defined. And then this sideways horseshoe is a symbol for subset. So the open interval u is a subset of the domain, meaning that the open interval has to lie entirely within the domain of f. So let's do an example. So so we can just really think about the domain. So let's say that we have an open interval on which the domain is defined. So the domain is defined on this open interval from, let's say, 1 to 3. So any point on the domain is an interior point. Actually, let's make it a closed interval. Why not? So let's include the points 1 and 3. So the domain of f in this example is equal to the closed interval from 1 to 3. Okay, so any point other than 1 and 3 are interior points. So for example, 1.1 is an interior point because I can take an open interval like that contains the point 1.1 and itself is contained on the domain. Now you see what happens at 1 and 3. So at 1 and 3, that does not work. So if I try the point 3, any open interval, no matter how small, steps outside of the domain. That's because the point x is equal to 3 is right on the edge, right on the boundary of the domain. And so any open interval, regardless of how small it is going to have half of it be outside of the domain, or part of it outside of the domain, part of it inside the domain, right? Because the point 3 itself is right on the edge of the domain. So those points are called boundary points. So we say a point on the domain of a function that is not an interior point is called a boundary point. So basically, for this example where we have the closed set from 1 to 3, the points 1 and 3 are the boundary points. Call it BP for boundary points. And again, that's because any interval that contains the point x is equal to 1, any open interval has to have something outside of the domain. Whereas that statement's not true for any point between 1 and 3, exclusive of 1 and 3 themselves. Any point like this, I can put an open interval around it, and that open interval is within the domain of the function f. So basically, the interior points, if you move a little bit to the left or a little bit to the right, you're still in the domain. A boundary point is a point that a little nudge one way or the other, you're stepping outside of the domain. So it's kind of like the boundary points are like the walls of a house, and the interior is the air between the walls. So when you're right at the wall, a little bit that way and you're outside of the house, whereas a little bit this way, you're inside of the house. Whereas the points inside of the house, if you move a little bit in either direction, you'll stay in the house. So that's the interior points and the boundary points. And it's really not a definition of a function, even though I cast it in that way. It's really an interior point of a set. So whenever you have a set of numbers, you can have an interior point to that set and a boundary point. However, we're going to exclusively think of these sets being domains of a function. So we'll always be looking at a point in the domain that's either an interior point or a boundary point. So boundary points are basically the edge of a function. And so one last quick picture of everything. So here's a function. So this point is a boundary point because the function stops there. And then this point is a boundary point, again, because the function stops right there. And everything in between is interior points. So in between that point and that point. So from here to there, the open interval, these would be the interior points. Our critical points are going to be, let's do a different color, right here, critical point, and then right down here, critical point, right? Zero slope, zero slope. There are no discontinuities, no kinks in the function, so there are only two critical points. Here I have zero slope, down there I have zero slope. Now notice next that the minima, there's a local minima, and the local maxima occur at the critical points and the boundary points. And that's essentially the context of our theorem that we'll see in our next video, the local extremum theorem. So basically, we'll have a result in a moment that guarantees that whenever you have a local extremum, so that is a local minimum or a local maximum, they always have to occur at critical points and boundary points. So as long as you know the critical points of your function and the boundary points of its domain, you can always track down the local, all of the local and minima and maxima. And if you know all of the local minima and maxima, then you can find the global minimum and maximum, or the global minima and maxima in the event that there are more than one. So now that all the terminology is in place, in our next video, we'll see it all in action with our theorem. So we'll use this. It's really, you know, sometimes the mathematical wording, it's meant to be precise. It's not supposed to be confusing. If you get lost in the precise definitions, just look at the picture. The boundary points are just the points on the edge, and the interior points are the points in between. The critical points, hey, it's a flat slope there, a flat slope there. Those are the critical points. If we have a function like this, that point where there's a discontinuity, also a critical point. Well, actually, yeah, let's put a point in between. So this point right there would be a critical point. And then if there's a kink, that would be a critical point as well. So, right, so basically that covers all of the types of things you can have. And so next we'll do our theorem that brings this all together, and then we'll do some examples of how to actually apply this.